the wonderful world of impact loads. So last time we were talking about how to whole computing strain energy for, say you had a cantilever beam and you had a block. Actually we did something in compression. Actually, I forget if I got here last time. Did we get to a cantilever beam or just to a block dropping onto just a brick dropping onto a support?
I think we talked about it at the end of class.
Okay.
Very end of class.
Okay. Okay. Well, in that case, where's my other piece of paper here? All right, sweet. Oh, yeah. I remember that now. Okay, so he had definitely talked about just a brick dropping onto some sort of support, right? That we do. Thank you. And here's so definitely he got that. We said something about strain energy in axial compression being something like that. Yeah. Where, yeah, P is that. Yeah. So it's called. So we got something like that, and the idea was, okay, that's cool, but it'd be neat if we could. It would be neat if we could drive this into other forms of stress too. Like bending in stress. So if we looked at that instead, so we just have some cantilever beam, because that's a pretty straightforward herd problem. We have some cantilever beam. We have our expression for strain energy density. Which was something like that, right? So it shows strain energy density being like the amount of strain energy per unit volume, and if you futz with the substitutions, you can work that. You can work your integral of force with respect to distance into something, and that should be epsilon x. In something with stress and strain in it. Okay. I'm just jumping kind of straight to there. And if we have, and if you have that, we can make we made some additional substitutions last time to get that integral to look something more like this. You have where this is strain energy, not strain energy density anymore, equal to the integral over a vol over volume. You have some normal stress, because that's what bending stress generates, right? Divided by twice the elastic modulus. Now this sort of helps us, but not really, right? Because we still don't have, like a volume integral isn't something that you can just analytically look at and say it's going to be blah, right? So what we can do is start substituting in for different things here, because if we maybe can substitute in for stress with some of its constituent values, maybe if we can divide volume up into something more manageable, maybe we can make this integral something that we can actually play with, something that we can actually integrate. So let's see what we can do. So if we have U equals the volume integral normal stress squared over twice Young's modulus dV. if looking at bending stress, we know that in bending, that's a pretty familiar sight, right? So we can substitute that guy in. This is a U, and it's the same U that's here. Capital is strain energy, so you might think of this as having units of like Newton meters. And lowercase would be a strain energy density. So it'd be like energy per unit per unit volume.
And big U said was just strain energy.
Big U is just strain energy. If I ever draw a small U, it'll have a tail. Yeah. Cool. Cool. All right. So we made so we can make that substitution, and we can also say, well, dV of volume is really like a differential area times a differential length, right? That'd be like a differential that'd be like a differential volume. So we can also split that up into like a dA dx kind of thing. And now we can start playing. So is there anything in here that we can simplify out? Anything here that looks like me smushed together? Okay, like substitute that in for M? Yeah, you could, but let's focus on getting some of the other kind of weird terms out first. Like, is there anything that we can do with a Y or a dA? Like a Y squared dA? Is that any physical quantity? Say again? Not quite. If you remember from bending, like what you call it, integral y dA was your second moment of area. Was your second moment of area. So we can actually say that y squared dA is I here, and simplify all that stuff out. So instead, get something like that. And that's a 2, I promise. Which is at least it's a little bit nicer, and like you're saying, we can replace the m squared with a force and a distance. And get something like that, where it's a px squared. It just won't let me write on that line for some reason.
Like px squared c squared.
Or p squared x squared, yeah. However you want to float that boat.
Also, I mistake what those units of big U.
And it has units of energy. So joules, Newton meters, foot pounds, inch pounds, whatever your favorite force times distance is. Yep. Calories. Want to be strange. Anyhow, so okay, so we have this expression for strain, which call for strain energy of a which is called for strain energy in pure bending. So if we wanted to apply this and integrate that, say that this beam is like a length L, we could evaluate this integral. What is going on outside? If we wanted to look at the maximum bending stress here, that'd probably occur here, right? Right at the root. So we'd want to integrate across the entire length of the beam. You might think that if I'm integrating from 0 to x, and I only look at a very small portion of the beam, I'm not going to have a lot of strain energy, right? So you might also to equate that with with like an area that would have like low bending stress. So like that would be a small x, because you get a small amount of strain energy and there's a small amount of bending stress there. Make sense? Hence we'd expect that physically, he's speaking. We'd expect there'd be only a small amount of bending stress here, which would correspond with a small amount of strain energy. So if we're looking for the maximum stress, then which would correspond to the maximum strain energy, we'd want to integrate to the point of maximum stress, or across the entire beam, in this case from 0 to L. So if we do that, so the maximum U, integral from 0 to L, p squared x squared 2ei dx. And would you mind closing the door, please? Thanks. I don't know what they're doing outside, but I'm okay with not hearing it as much. So if we integrate this guy, what do we get? Say again? Almost. So here we got an L cubed, because that x goes to cube, you got a 6. But the p is a constant, right? So it should run a square. So we get something like that. It's maximum mu. Cool. And really this load here, this P, this force, is more like an equivalent load, right? It's there's we're solving this via some we found this P, this load, this didn't come from an actual force pressing down on the bar. This came from the definition of energy. So this load is more like more like saying, okay, this brick is going to hit the bar with some amount of force. It's going to transfer some amount of energy, whatever energy that it has, it's going to give to the bar. That's going to be equivalent to some force acting at the end of this bar and pressing down. So this is really an equivalent from force acting at that point. And like we said, this is kind of like the worst case scenario. This is because all this is only valid for an inelastic collision, because we're assuming that all the energy of this guy is transferred to that bar. All right? So how might we actually use this? So one example would be if we can find out what this equivalent force is, then maybe we can start solving for some stresses. Because like if we have a force acting at the end of this bar, we can find like a bending moment over here at the root. And if we have a bending moment, we can get a stress. So you might think of our goal is to fill as what's called as getting the P in that equation, or if force at the end of this bar would be some P equivalent acting at the end of that bar. And this would be like a P equivalent. All right, so for that that one we can do, right? Because if we can take this and solve for it. So you have some like P equivalent equals what? 6 EI U max over L cubed, square root all that stuff. And then we can just substitute that in. What might we use for U max? What might we use for that amount of energy?
MGH.
Okay, MGH, what's the assumption built into that statement?
It will transfer all of its energy.
Okay, the brick will transfer all of its energy. What other assumptions are built into that statement?
Has mass.
It has mass. I'm glad that has mass. What other assumptions are built into that statement? Put it this way. Why are you saying MGH?
Because that would be gravitation.
Okay, so you're saying that the only kind of energy that it has is gravitational potential energy. Is that correct?
It's getting dropped on.
Okay, so whatever energy this guy has, you can think of this as just an energy source. Whatever energy that has is being transferred, and that's what Umax is. Because whatever strain energy you get in the beam has to come from somewhere. First law of thermodynamics, right? So if we're thinking of this brick as your energy source, whatever energy it has, potential, kinetic, whatever, we're saying gets transferred into this term. So by saying MGH, that's just saying that it's a brick that's dropped from rest. If it was like a bird flying at 80 miles an hour, then you'd have some which called kinetic energy too, right? So that's what I wanted to say about that. But once you have what this value is, you can get what your equivalent load is. You have your equivalent load. You can figure out what your bending stress is. And from there you can play all your regular Moore circle games and what have you. Yeah.
So you use MGH?
You can. It all depends on what your situation is. If it's a brick that I threw at it, then it's going to have some MGH plus half mv squared or something like that, right? If it's a brick that I just kind of drop, then it's pure gravitational potential energy. If it's a spring expanding into a beam, kind of like a car's, what's called shocks, then it's going to have like a 1/2 kx squared energy being transferred. It all depends on what your situation is.
And that also, what does it say to the left of the PEP in the Umax equation?
Umax. That is a arrow that I didn't fully erase. All right. Any questions on that? Cool. So congratulations. That's the end of the material that'll be on the final exam. Enjoy. And for the rest of the class, had two things. One is that if you had questions on stuff, I'd be happy to work through them. Or if not, I had a problem or two to play around with. So, any questions?
How important is the wall vessel things for our final?
The what vessel?
The thin.
The thin wall pressure vessels?
Yeah, is that important?
You probably should know it. Yeah.
Do something with that, please.
Oh, okay. Sure. What part about it? Just how it's called, just analysis of.
Anything that we might need to know. There's more.
All right. Well, we'll do a problem anyhow. Let's see what happens. Let's see. There we go. Anything on the email that I sent out the other day is important for the final. All right. So let's do this one. Wish I had my chair up here still. All right. So, all right, it's that one. Okay. Side, front. Da, 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 da. Okay, it's got some pressure vessel with a 30-inch outer diameter. Some length excluding the end caps. That should be more circular. Feet there. Do 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 do. Do 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 do. Okay. Some internal pressure. 180 psi gauge. Okay. Wall thickness. 3/8 inch. Okay. So I guess I could put that onto here. All right. So, first things first. Does this meet with thin wall pressure vessel assumptions? Why? Prove it. Prove it.
3/8 of an inch is less than 10 times 30 inches.
Say again?
It would have to be, it could be 15 inches. It could be 1 inch. Yes, 1 inch.
Okay. So, okay, and your rationale for that is? I didn't hear your first statement.
It could be 1 inch thick, and they would have a ratio of 1 to 10 of thickness to radius ratio.
Okay. So, you're saying that that has to be greater than 10, and here it's like 15 over 0.375?
Yes.
Cool. Yeah, that's which is greater than 10. And in fact, you'd have up to 1.5 inch thick wall, and it'd be fine. So cool. Okay, so this meets with that assumption. What are the other assumptions of a thin wall pressure vessel?
It has pressure.
It has pressure. What kind of pressure?
Uniform.
Uniform. Is it uniform? What do we have inside of here?
Okay.
Okay, so we got some sort of gas inside of there. As long as you have a gas, means that we'll probably have a fairly uniform pressure distribution that satisfies that satisfies that assumption. We also have a uniform cross section and all that kind of thing. So that satisfies those assumptions as well. All right. So this is a thin wall pressure vessel. We can analyze it now. So what are the ways that this thing could break?
Like the
Radial pressure.
hoop stress thing.
Okay, so and so hoop stress is looking at what failure mode. How is hoop stress assuming that this thing's going to come apart?
They would burst out the short waves.
Short waves. Okay, so if we had, so it'd be like cut this in half, it would be exploding sideways, right? So that's what hoop stress is looking at. So if we did a section here, and so these are two views of the same thing. All right, so this is like looking, so this is like this is like a sectioned front view. This is like a sectioned side view. All right, so let's be like T, let's be some dx. This has some pressure P. All right, so how do we analyze this? We could derive something, right? I mean, that's totally fair game. Alternatively, we already have something derived, right? So what do we got?
Stress equals PR over T.
Stress is for hoop stress, right? So we know that hoop stress, well, hoop equals PR over T, so we can find that kind of stress right off the bat, and that'd be stress kind of tangential to the tangential to the circumference, right? Does that make sense? It's kind of like a circumferential stress. Say again? Not in this case. Not for this particular free body diagram. If we say that it's going to burst apart horizontally, or burst apart laterally across the short direction, then then the stress is being reacted on these things, right? Which means that it's going tangential to the circumference. All right.
So is it 15 or would it be like 15 minus 2?
Right. So if you're on the outside here, if you're on the outside, it'd just be the outer radius. If you're on the outside here, what's the gauge pressure acting on that point in the radial direction? What's the gauge pressure of atmospheric conditions? Gauge pressure, not absolute. Zero, right? Because gauge pressure is absolute minus atmospheric. That's the definition of gauge pressure of gauge pressure. So because this is always a gauge pressure, that means that the how do I want to say this? Sorry, let me try to not mislead you here. I'm talking about two things of the same at the same time. So that here's, so this piece is the internal gauge pressure. So the pressure of whatever's being carried by this thing. And that gives you the hoop stress. Teresa asked about what about radial stress. So if I'm on the outside here, the amount of radial force that's acting on that point, if I'm thinking in terms of gauge pressure, because I've already kind of accounted for atmospheric conditions by using a gauge pressure here, on the outside, the radial force, and therefore the radial stress, is zero based on that sort of an idea, because if we're looking at the gauge pressure of the atmosphere, it's zero. If I was sitting on a point on the inside, radial call it radial stress. What's called the radial stress there would be different, right? What pressure is what pressure is pointing directly out? P, right? So I can call your sigma z, if you will, or your radial stress, your out of plane stress, equal to the pressure on the inside, but on the outside it would be zero. This would be, again, this would be gauge pressure. Or both those things are the same thing. All three of those things are the same.
Which is pretty low.
Yeah, relatively speaking. 180 psi is not that big of a number.
So R would be diameter over 2 minus d.
Depends on where you want to look. If you wanted to look at the stress on the inside wall, then yeah, it'd be OD over 2 minus T. If you want to look on the outside wall, it'd just be OD over 2. Okay?
But then the stress would be 0 because P is 0.
Remember, this is internal gauge pressure. No matter what, these walls have to react the force created by that pressure, no matter what, right? Like if we don't want this thing to blow up, they have to react that pressure, whatever force created by that pressure. Therefore, that P is always the internal gauge pressure. The only thing that it being inside or outside changes is what your radial force is. So if, say, you were trying to find stress on the outside wall, your sigma z would be 0 because there's no force there, because the gauge pressure is 0. If you're on the inside wall, your sigma z will just be equal to your gauge pressure, to the gauge pressure of whatever gas you're storing inside of this thing. And if you're actually, we'll get to that difference in a second. All right, so we clear with that?
Yeah.
All right, so we got hoop. So we got hoop stress, and can someone punch me out a number for that one? Let's look for it on the inside wall, just for kicks and giggles.
Is the radius from
70-20 what? Cool. Oh boy. Remember on the inner wall. So it's 15 minus 0.375. Because the diameter is the outer diameter.
Yep.
What do you got?
7.02.
Okay. So we got a hoop. So we got a hoop stress. This is on the inner wall. Cool. All right. So that's one way that it's going to break. How else is this thing going to break? How could it break, anyhow? Longitudinally, right? Because it got caps holding everything in. So got something like that. If we take a section through some arbitrary location along the length, got some pressure for force there. How do we get longitudinal stress created by the force? All right, so PR over 2T. Again, if we're looking at the at the inside of the cylinder, what's that stress? If someone could punch a number for me. 4230. All right. Why you should see? Yes. We did this on the inside, so we should do this on the inside.
No.
Nope.
Yeah.
0.551 KSI, because that's half a hoop stress. Cool. All right. So we got that, and we said before, because we're on the inner wall, sigma r is equal to pressure. Cool. So because that's what's called because that's the distributed force at that point. Radial stress. Yeah, like what's called kind of like we were saying. At this point, you have some out of plane stress, and we just computed some in plane stress. So this is your out of plane thing. Or if you wanted to look at it on like a stress cube kind of thing, and you call this like your x direction, this your y, and this your z, and you said like this is my hoop stress direction, this is my long direction, this would be like your radial direction. So we have all normal stresses, but it's a very 3D load state. And if we weren't on the inner wall, if we were on the outer wall, radial would just be zero. The radial stress would just be zero, and we'd be left with just straight up plane stress. So sigma z would be zero. We only care about this in the in plane stuff. All right, cool. So let's play with this. So we have three stresses, and if we wanted to like compare this to something meaningful, like a yield stress for the tank, what do we want to do? Stress transformations, yes, because then we can get one. Because then you kind of combine all these to get one number that we can compare against. That's kind of the thing with all yield theories. Like if you look at von Mises, which is a more common one, it's all just trying to put all these different stress contributions together into one number. So if we wanted to make more circles with this, how would we do it? Say, didn't hear a word you just said.
We put down those principal stresses on the x-axis.
Okay, why are those principal stresses?
Those are the principal directions.
Why are they the principal directions?
They look pretty principal.
Fair enough. What's the definition of a principal of principal stresses?
Stresses that are in x, y, and z directions.
Okay, so they're purely normal stresses. The principal stress state means that you only have normal stresses. There are no shear stresses. Do we have any shears? Do we have any shear stresses? No. So these are the principal stresses. So you could do your Mohr circle equations and say like, okay, sigma average of these are your in-plane ones, right? So do sigma average equals like sigma h plus sigma l over 2, and your radius is like the square root of difference between those over 2 squared plus tau xy squared, blah, blah, blah. But if you do all this math, you're going to get a principal stress where sigma h is. You're going to get a principal stress where sigma L is. And then we said if there's no shear stress, the last guy, called this is your third principal stress. Okay? That makes sense to everyone? So, yeah. Yeah. So, for a thin wall pressure vessel, it's somewhat simplified. Now, what are my circles?
Circle between the R and the L.
There are three circles. Yep. So, yep. That's a terrible circle. But then that becomes my maximum shear stress. I can find that just by doing some just by doing some geometry, because I know what the diameter of that circle is, so I can find its radius and so on and so forth. And that number I could compare directly to a yield stress. Yeah, sure. What's that number?
3.42 KSI is the radius.
3.42 KSI is the radius, so the diameter here, or from there to there, would be like sigma h minus sigma r, right? And that'd be like 0.684, something like that. Yeah. Okay. So with the point moved over. Something like that. So that's the diameter. So radius would be half that. So 3.4442 KSI, or the maximum, which should identically be the maximum shear stress. And then if you know what the material is, so like if it's A36 structural steel, you can look up the yield stress as being 32 KSI in tension. And you can say, hey, we're nowhere close. It's called nowhere close to it. In fact, we're almost a factor of safety of 10, which is good for an application like this.
So you would do which one is
Yeah, so so the definition of factor of safety is what? Sigma whatever limit that you're using, over whatever your actual amount is, or your allowable amount, however you want to play this game. Yeah, so you have like 32 divided by 3.42 equals your factor of safety. Okay. Now, if this is on the outside, what would change if you're looking at a point on the outside of the pressure vessel?
We would lose one of our principal stresses.
Okay, and it would be 0, right? Yes, both your hoop stress and your longitudinal stress would change because your radius had changed by a small amount. So it'd be almost the same, but slightly different. Yeah, slightly larger. So you could recompute those, and once you had those, you can draw your 3 circles again. The only difference being that sigma r is now at 0. And you have your new numbers for your longitudinal and your hoop stress. Okay, was that all that you wanted? Cool. All right. Any other questions with us?
So the length of the vessel doesn't matter
Not really.
unless they like gave you some sort of moles of gas and you had to figure out what pressure that would create with the volume.
Yeah. Yeah. Yep. Or if there was something like like this vessel was made by some helically wrapped piece of metal or fiberglass or something like that. But I'm not going to be that crazy. Welcome. I'll just be crazy in other ways. All right. Well, that's all I got for today. Thanks.